Thanks everybody for the presentation from Rightful. Now we have Alexander Montgomery Cochrane from Heronic Technologies, co-founder and CEO of Heronic Technologies. Prior to starting the company, he completed his PhD at Imperial College London, researching methods for accelerating AI on FPGA devices.
Brilliant, thank you. Yeah, so Heronic, we're a .ai, so we're relevant in 2020. And we're automating the design of bespoke AI hardware. I'm sorry, guys, this isn't verification, but we do use FPGAs, so there's that.
Sorry.
No worries. There we go. What's the problem? Just broadly, AI is costing the world. If you think about, LLMs and how the scale of AI is growing, we're taking on more and more energy to produce these inferences, to run your ChatGPT queries, and it's predicted to reach 1,000 terawatt hours of energy by 2030, equivalent to Japan. These are enormous numbers, right? So we need to do something to address the scalability of AI. And what's a better way to run AI if it's not in data centers? It's at the edge. So we're running these AI models on smaller, more efficient devices. And what are the problems with this? So in general, with AI hardware, but specifically with edge AI, there's this utilization problem. And I'll give you this one example. So this is from MLPerf. I'm not going to name and shame the hardware here, but we have this enormous potential for performance. So 2,000 teraops, 2,000 tera operations per second that this hardware is capable of. However, when you use it for any particular workload, you're only using 35 teraops. It's just a tiny fraction, less than 2% of the device is actually being used. And so as engineers in the room, you can see there's this optimization problem to be had. There's this efficiency that we're leaving on the table. In general, there's this rising potential. You hear about NVIDIA's Blackwell GPUs. You see these massive numbers in terms of what they're capable of. If you look at the trend over the years, there's actually this diminishing return on this performance. So this leads to a number of issues. You have this low energy efficiency because you have all this static power that's being dissipated for nothing. Poor performance, obviously you're not getting everything you want. And overall, it's expensive. It makes running these chips more expensive. Our solution is to automate the design of this bespoke AI hardware. So we treat it as an optimization problem. We take a specific AI model or a family of AI models, a target technology. So in the context of this room, it would be a specific FPGA device, and an objective described in terms of power, performance, and area. And internally, we have this design space exploration tool that we have our library of primitives which are all parameterized, and we have our solver to go and find the optimal configuration for this problem. So we're producing what's objectively optimal hardware for our given design space. So benefits, rapid design cycle, high efficiency, very low latency, and so on. And why is this a better approach? So very abstractly, GPUs and NPUs, this is a go-to hardware at the moment, and they're more of like a one-size-fits-all type of solution. So you imagine you're taping out this one chip, or you're designing this one accelerator for all of these different problems, and you're casting this wide net in terms of what you're able to support. And that means that you're losing out on this efficiency for any of these particular workloads. What we're working towards is this specialization towards the specific workloads that you want to run. So really filling in and making the most out of whether it's object detection, super resolution, and so on, making the most out of that hardware. So I'm going to go a bit into the architecture itself. But as a kind of background to this, so when I was mentioning GPUs and NPUs, they follow, well, NPUs in particular, they follow this systolic array style of architecture. So you have this array of processing elements, which typically essentially multiply accumulate blocks. You can see it's this homogeneous array of processing elements. It's more of an overlay style of architecture. So you have the single engine that you're computing across. Software execution looks like an instruction-based architecture. You're running first layer, sending in some feature maps, sending the output, and executing this, layer by layer, operation by operation. Because of that, you're keeping a lot of your data off chip. So there's this massive overhead when it comes to sending and receiving off chip memory. In terms of, pipelining, so pipelining only happens within the layer itself, and there's no, for that whole AI model, there's this discrete boundary where you need to keep everything within each layer of execution. What we're designing and the general style of architecture is this streaming architecture or streaming data flow, where instead of having this homogeneous array of elements, we've designed something a lot more heterogeneous that fits to the specific problem. So you can imagine the hardware compilation, it's bespoke to this particular application. From the software side, because we're implementing operations directly in hardware, it's hostless. There's no instructions to send. It's just start going and keep operating. And so you get this efficient memory map. We have this hybrid approach to storing on-chip and off-chip memory. We're pipelining not just within a single layer, but across the whole network itself. It's just if you're familiar with AI engines, instead of it being each layer having their own separate time multiplexed operation over the hardware, instead we're running concurrently all of these layers together, and it's deeply pipelined. So you get this very low latency where the final layers are executing while the first one's still processing, the start of that feature map. And then I'm going to talk a bit about how we actually find these optimal architectures. So here's a kind of overview of how we go about the design space exploration. So we start off with our specific AI model and FPGA that we wish to target. We have this library of parameterized RTL blocks, which are essentially these building blocks, these components that we can compose together based on the application that we're targeting. So you can imagine with each of these design points, if you were to put it through Vivado to get the resources from synthesis or place and route, can take forever, right? Each of these design points would probably take many hours to collect. So we have a set of high-level models, both on the resource and performance side, to take it from hours to milliseconds in terms of estimating performance. So that allows us to rapidly evaluate whether the design is meeting an objective. And compared to more, I guess, traditional processors, we have these explicit metrics that we want to achieve. So we're feeding in what exact performance, or what are the bounds on performance, power, and so on. And so we can objectively evaluate whether we're reaching what we want from this design. And then, of course, we're using AI to drive our design space. So we have this ML-driven, basically, we're looking for the next best design, and we're using these metrics and our own heuristics as well as AI techniques to come to that next design point. And so what is it that it's actually modifying within the hardware itself? So the first stage is taking this abstract, this graph of operations, which is the AI model, and mapping it to intermediate representation of these building blocks. We then, as part of this design space, explore different levels of parallelism within these building blocks. So it's essentially like a trade-off between performance and resources, but instead of having to manually discover that optimal trade-off, we're exposing that to the optimizer itself. You can imagine that within, say, this is an example of our convolution hardware. We have all these, discrete building blocks with parameters such as level of input parallelism, output parallelism, and so on. These are all variables within an optimization problem. Next part is quantization. So I'm not sure if you're aware, but with AI workloads, you're not constrained to floating point or other specific scientific representations. So we've exposed the quantization, the word length, as a design point as a variable in our design space. In here, I'm going to show off a bit when it comes to our performance. So we did the MLPerf Tiny benchmark. So this is a benchmark specifically for tiny ML models. So this is keyword spotting, anomaly detection, and so on. Showed really good performance, the lowest latency out of for 3 of the benchmarks out of 24 submissions. Yeah, it shows us. So we were using, I believe, is one of the smaller Zinc FPGA AMD devices, and we were showing this quite interesting trade-off between energy and performance. So we weren't quite at the ASIC level when it comes to energy, but we are, really pushing the performance and on the inverse of that latency. And what was particularly interesting to us is AMD's solution. We're comparatively a lot higher performance for what is a similar technology, a similar FPGA, or the same FPGA even. We could show better accuracy, lower latency for the exact same benchmark. Another proof point is object detection. So so with object detection, there's this popular family called YOLO. So you only look once. And the challenge here with this model is it's a very large parameter space, very heterogeneous architecture. So it's not just one operation after the other. There's a lot of these interesting skip connections. And so we showed that through design space exploration, we can find this Pareto optimal set of design points compared to what's out there in the research. And we also found that we can show very good performance compared to a similar process node NVIDIA device, similar scale as well. So there are these advantages for using FPGAs in particular, but also by automating this design space and leaving this tool to find what a human wouldn't necessarily think to look for in an architecture design. That's it. Thank you for listening. And any questions?
Good. Are you still in time today?
Yeah. Okay,
any questions? I see there's questions online. I've got a couple of questions here. So the first question was, what advantages do FPGAs pose compared to GPUs and NPUs?
Yeah, interesting one. I think something that we tend to neglect with FPGAs is the reconfigurability aspect. I feel like in general we treat FPGAs as like once you've done your design, it stays stationary. That's what we're pushing out, but at least in the AI side. But what we're making use of is the fact that you can specialize down towards a specific AI model. You can specialize down towards a specific accelerator and change it in the future. If something happens in the AI space, you're able to go and update and stay up to date with what's state of the art.
Okay, and I've got another question from the audience here. Which AI applications benefit most from FPGAs?
We found super resolution. It's quite works quite well with our style of architecture. I feel like FPGAs in general, at least from the AI side, suit computer vision models a lot better than what GPUs can do at the moment. But we'll show more in that space as we keep progressing.
Perfect. Thank you very much. Thanks.